For the final example problem of this chapter, we are told that you are lying on a beach and you're watching the waves crash onto the sand and recede back into the ocean. You see the sun begin to set below the horizon, and as the last little sliver of sun dips behind the horizon, you decide you're bored, so you quickly stand up. 11.1 seconds later, you get to see a second sunset, and you're going to use that to determine the size of the Earth. So how on earth are we going to find that information out? To begin, we don't know what we're doing. Let's just draw a picture and see how that directs our thinking. When I draw a picture, I'll draw the first sunset, the second sunset. I'll draw myself lying down and standing up. And from there, that might help us think about this problem. So let's say here is the Earth. This picture will not be drawn to scale. And let's suppose this picture of the Earth, we are looking from above the North Pole. So the Earth, we'll say, is spinning like this. And we'll say the sun is really far away this way. So to the sun is going to be there. Now, where was my eye the first time I saw sunset? Well, the first time I see the sunset here, my eye would have to be right here. Because if my eye is over here, well, the sun has not set yet. And if my eye is over here, then the sun is already behind the horizon. So the moment the sun sets, when my eye is at water level, right on the beach, my eye is right here. And I look at this picture and I notice my eye is a distance away from the center of the Earth equal to the Earth's radius. What then happens? We stand up. As the Earth will continue to spin, so we stand up, and 11.1 seconds later, we are standing up, and we are able to see a second sunset, because we are able to, due to our non-zero height, peer over the horizon of the Earth and look out towards the sun. So at this point, I look at this picture and I say, well, we know our height is 1.7 meter. So this distance here is 1.7 meter. And this distance here will again be the radius of the Earth. So if I look at this picture and look at it carefully, as I said, this picture is definitely not to scale. If this were to scale, you would be much, much closer, but you can't really see it on a drawing on the board easily then. I notice there's a right triangle in this picture, where the one leg of this right triangle has a length r, which is the radius of the Earth. The hypotenuse of this right triangle has a length r plus 1.7 more. So the hypotenuse is going to have a length of r plus 1.7. And this distance over here is the distance I have moved away from the sun in those 11.1 seconds. I do not know what that distance is. So without more information, I'm just going to call this distance d. So at this point, we remember from geometry the Pythagorean theorem, a squared plus b squared equals c squared. So in this case, the two legs of my right triangle, a and b, are d and r. The hypotenuse of my right triangle is r plus 1.7. So if I could find a number for d, or if I could even just somehow write d in terms of r, that will be good enough to completely solve this problem. So my Pythagorean theorem in this case would be written as r squared plus d squared, the lengths of the two legs of the triangle, and I square the length of the hypotenuse. The total length of the hypotenuse is r plus 1.7, and that is what I have to square. It would not be correct to write r squared plus 1.7 squared. I need to square this entire term, which means I will need to do a FOIL when I do it. So this is the picture I have. What is this distance d now? I don't know. But let's think about what we do know. We know that this sunset occurred 11.1 seconds after this sunset. So this is 11.1 seconds later. We also know that the Earth spins at constant speed. The Earth doesn't change its rate of rotation in any meaningful way from one day to the next. So we know the Earth spins at constant speed. So I could say the speed is distance over time. And in this picture, in 11.1 seconds, I traveled a distance d. I started out here when I saw the first sunset. 11.1 seconds later, I see the second sunset. So I traveled this far in 11.1 seconds. So I can write the speed of the rotation of the Earth as d over 11.1. Now, this statement is not completely true, but I will explain what I mean at the end of this video. This is a pretty good approximation for what we're going to do. Okay, so I have d. I need to find something for d that I could replace it by. I could write d is equal to the speed times 11.1, but without knowing the speed that the Earth rotates at, that doesn't really help me. So, but still, let's think about it. How fast will you move? You're traveling with the Earth, so how fast is the Earth spinning? How about we think about it like this? We know we traveled this distance in 11.1 seconds. Is there another distance that we travel in another interval of time that we can write that either will give us a number explicitly or give us some numbers and some factors of r? So if I think about it, I could look at this and say, well, in 11.1 seconds, you went from here to here. In 24 hours, you will go all the way around once. So this will be in 24 hours. So let's use this idea. If the speed is constant, I could also write the speed is equal to the distance traveled around the Earth once over 24 hours. Because we're going from here, we're going all the way around once in 24 hours. Well, what is this distance traveled? I look at this picture, and the distance I travel here would be a circle. So the distance traveled would be the circumference of the circle. So I could write the speed that I'm traveling at would be the circumference of the Earth over 24 hours. Do I know the circumference of the Earth? Well, I don't know what that number is, but can I write the circumference of the Earth in terms of the radius of the Earth? Yes, I can. In general, for a circle, the circumference is 2 pi r. That would be a number you could just look up in a textbook or Wikipedia or something. So I could say the speed that I'm moving at here would be speed is equal to 2 pi r. And 24 hours, if I convert that number to seconds, I get 86,400 seconds is 1 day. So 86,400 seconds. So I do not know what the speed of the Earth is, but I can write the speed of the Earth in terms of the radius of the Earth. I know 24 hours, you convert hours to minutes, minutes to seconds. You eventually get this number, 86,400 seconds for 24 hours. Okay, let's compare. We said this speed of the Earth is going to be the same. The Earth doesn't change its speed as it rotates. So whatever this number is, this number has to be the same thing. So I could write this as d over 11.1 is equal to 2 pi r over 86,400. Because this speed and this speed must be equal, So I could say this term must be equal to that term. Now at this point, I have a way where I could write D only in terms of my unknown, only in terms of R, and then I have enough information to finish this problem. So I could write this as this distance D that I do not know what it is, I could write as D is equal to 11.1 times 2 pi r over 86,400. And now I have D written explicitly only in terms of r. I could plug D in right there. So at this point, my Pythagorean theorem would look like r squared plus, I do not have a calculator on hand, so I'm not actually going to solve what that number is going to be. So I will write it as 11.1 times 2 pi r over 86,400 is equal to r plus 1.7 squared. Now notice, this entire equation, I have a whole lot of numbers, but this only has r in it. So this equation only has the radius of the Earth, and at this point we have enough information to solve it. So at this point, I am going to stop doing this problem. Leave lines in your notebook to finish this problem. 2 hints I'm going to give you. This number you will need to FOIL. In my opinion, just find a whatever decimal number this is going to be. I don't know what it's going to be. It looks like it will be some small decimal number. And when you calculate it out, just round to the 3rd significant digit. Don't write giant strings of numbers because that's annoying to work with. And after that, you then will use the quadratic formula. So after this, use quadratic formula. To find r. And from there, you will have enough, you will be able to then plug numbers in and find the radius of the Earth. Okay, so I told you that this D is technically speaking not quite the distance we travel, but it's a very subtle thing and not going to be very significant. Why is that? Well, if I just grab a different color marker, I assumed when I was talking about the speeds that the distance traveled was this line here. Strictly speaking, I shouldn't be allowed to change my position, so I should have been, when I was talking about speed, talking about the distance of this arc. And this arc along the surface of the Earth is not going to be the same as this D here, but it's going to be very close because we're comparing 11 seconds to 86,400 seconds. So this arc will be practically equal to that distance D. So it will be a slight correction, but not anything significant for this problem. So as I said, finish this problem on your own. Don't forget to FOIL that guy, rearrange it, simplify the equation somewhat. Eventually you'll get something like some number times r squared plus some other number times r plus some other number equals 0. And then you use the quadratic formula to find what r is equal to.